So now we are shifting to the coding part, the programming screencast part for the chapter cascading behavior in networks we have discussed just now. What we'll be doing here in these programming screencasts is we'll be taking the major concepts that we have discussed in this chapter. So I will be taking 4 major concepts that we have discussed in this chapter and we'll be coding and validating all those 4 major concepts one by one. So I'll quickly recap these concepts for you and then we'll start with the coding part. In this entire chapter, we talked about a particular scenario. And the scenario was there is a network and on this network, every person has adopted some action or some behavior. So every person has adopted the same action or same behavior and everybody was living comfortably with it on this network. But then with time comes a new idea, new action or new behavior in this network. And then people start changing. This new idea or new behavior starts cascading on this network. So the example which we have discussed in the chapter is there is a network on a class, people in a class where all of them have initially decided to work in library on a pending assignment, And then came this new idea of going outside and having fun. And then slowly this idea started cascading and more people started going outside and having fun instead of sitting in library and working. So that's the exact thing which we'll be talking about. So as you can see that here is a network. Initially all the nodes in this network were blue. So they have adopted an action, an idea, a behavior. Let's call it a blue action, blue idea or blue behavior. But then comes in picture a red idea, a red action, a red behavior. And it wants to diffuse on this network. And then we have looked at the obvious problems with this. What is the problem with this blue idea, blue action, what is the problem here with this red idea to diffuse on this network and make all the nodes red here? The problem was, as we discussed, that people find it risky to adopt a new idea or a new behavior. They are not comfortable shifting to a new thing, especially when all of their friends are doing the old thing. So no node in this network actually wants to shift to this red idea. They find it risky to adopt. Then what do we do? What should this red idea do to diffuse on this network? And we have looked at 2 solutions to this problem. The first solution was to increase the payoff associated with this red idea, to increase the benefits associated with this red idea. As the benefit associated with this red idea increases, more and more people start adopting it. So you have looked at how we have modeled the entire thing with the help of payoff and number of friends. Each idea here, let's be it a blue one or a red one, gives you a payoff. And then based on that payoff and your number of friends which have adopted that idea, you decide what to do, right? So you increase the payoff associated with this red idea and probably it will cascade on this network and rather cause a complete cascade. What's a complete cascade? Complete cascade is when every node in this network turns red. This red idea is adopted by all the nodes in this network. We call it a complete cascade. We will be modeling it in screencast 1. Sorry. So what we will be doing in screencast 1 is we will take a network where everyone has adopted an old idea and then a new idea comes which is having some payoff which is obviously greater than the payoff of the old idea but still on a lower side, and we see that with this payoff this new idea is unable to cascade on this network. It's unable to cause a complete cascade on this network, but as we keep increasing the payoff associated with this new idea, finally it creates a complete cascade. We will be looking at it in screencast 1. So screencast 1 is associated with the first idea. You increase the payoff associated with this new idea. What is the second idea? What was the second idea that we discussed? The second idea was about choosing the right people. So maybe if you start with this node here, you are unable to create a complete cascade. Or if you start with this node here, you are unable to create a complete cascade. But if you start from this node here, which is very well connected to rest of the network, you might end up creating a complete cascade. So if you start with some nodes in this network, the cascade doesn't occur. If you start with some other nodes in this network, the cascade might occur. And I'm quite sure you remember this. We talked about this bike example. If you want a new bike, it should not be your mother here or your sibling here which you should be convincing. It should be your father. So this thing we will be discussing in screencast 2, where we'll again do almost the same thing. We'll have this network on which every person has adopted an old idea, and then this new idea comes, and now we'll keep the payoff associated with this new idea to be same. We are not going to change the payoff, but we are going to change the people from where this cascade starts, and we show that if you start from some bunch of people, it is unable to create a complete cascade. But if you start from some other bunch of people, it is able to create a cascade. So we'll be talking about it in screencast 2. Screencast 3. This very cute idea of the effect of community on cascades. We have looked at community traps cascades. So here if there are two communities and this idea originates here, it cascades, and this entire community has adopted this idea, but it is difficult for this idea to come and diffuse to this community. So one community remains with the old idea and other has adopted this new idea, and we have looked at the reason for why it happens. So we'll be coding it in screencast 3, where we'll take a network having two communities and we'll start our cascade from one community, and we'll see that it infects everybody in this community but is unable to reach out to this another community. In the last part, we'll be implementing the theorem we talked about. So the theorem was, the statement was, if there is a cluster of density greater than 1 minus q, a complete cascade is not possible. So many technical words here. I suggest that you go back and quickly watch what do I mean by cluster density 1 minus q here. I'll quickly recap it here. So we say that there are clusters in every network, and we say that a cluster is of density p if for every node in this cluster, each and every node in this cluster has at least p fraction of their friends in the same cluster, and we call it a cluster of density p. And q here is a threshold associated with the new idea, which means that if q of my friends, q fraction of my friends, or greater than q fraction of my friends adopt a particular idea, adopt this new idea, I'll also adopt this new idea. So the theorem said that if there is a cluster of density greater than 1 minus q in this network, then your idea cannot diffuse inside this cluster here. So here is a cluster of density greater than 1 minus q, and your cascade starts from here. Even if your cascade infects all these nodes in this network, all the nodes in this network, we'll see that it is unable to diffuse inside this cluster. And we have talked about the proof of this theorem in the chapter, but here we'll be coding it and validating it with the help of a code. So this will be our screencast 4.